Hi, thank you very much for coming back. Today we're going to be talking about quantum error correction. And so quantum error correction, from my perspective, is actually probably one of the most important features of quantum computing. And so I wanted to spend a fair bit of time talking about how this ends up working, because it's actually the thing that ends up making quantum computing a practical form, or potentially practical form of computing. The reason why is because at present, if you take a look at existing quantum hardware, the gates that we have, roughly speaking, have failure rates that are on the order of about 1-ish%, 0.1 to 1-ish%. And so what that means is that basically we're limited at present to computations that have 100 or fewer-ish gates, depending on the level of accuracy that we end up needing. Now, obviously, there's many algorithms that we've covered so far, and that we'll cover in the future, that require far more than this. So the ability to be able to either design hardware that is dramatically more accurate than existing technology allows, or giving us the ability to correct and detect errors in a quantum algorithm is absolutely essential for us to bridge this gulf between where we are currently and where we need to be in order to make quantum computing practical. And surprisingly, quantum computing is actually error correctable. Now, this is something that wasn't always obvious to the community. The reason why is that there's some big differences between classical and quantum computing, or at least some differences that seem quite big on the surface, as we've seen so far in this course. Such as, with quantum, whenever you measure the system, you run the risk of damaging it. So detecting the presence of errors is a lot more subtle with a quantum computation than it is with a classical computation. The next issue is that, of course, there's a no-cloning theorem. Well, there is as well for classical probability distributions, but that being said, that does prevent us from just abjectly cloning a quantum state and using this to create redundancy for our programs. And finally, the other thing is that errors in quantum are continuous. You could have an arbitrary unitary describing your error. In fact, you could have something which you could view as a probabilistic mixture of unitaries affecting your quantum computer. And that is very different from the bit flip model that people normally consider in classical computing. So I'm going to begin by first doing what I usually do when it comes to these topics, is I'll begin by talking a little bit about the classical version of error correction. And then what I'm going to do is I'm going to begin generalizing this and talk about how we can do error correction in a quantum setting. So today, what I'm going to be doing is I'm just going to be talking about building up showing how to resist bit flip errors in a quantum computer by encoding your quantum information in sort of a degenerate subspace of a higher dimensional system. And then what we're going to do from there is, next lecture, we're going to talk about how we can make this resilient also to random phase flip errors, and argue that once we have a code that can detect and correct both bit and phase flip errors, that actually it will be capable of correcting every error. Now, this is a totally unobvious fact, but it's key for us in quantum error correction. And the idea basically is that what quantum error correction does is, through measuring auxiliary parts of the system, it's actually capable of projecting arbitrary errors down to discrete errors that can be corrected. And this is the thing that's magical about quantum computing when it comes to error correction, is that while it has this continuous aspect to it, it actually can be corrected using discrete operations because of this property. But we'll get to this shortly. So let's begin by talking about the very first idea in classical error correction, which is one that you probably are already familiar with, but that's why I'm going to begin with it. And so the simplest way that we can deal with this is kind of majority voting, or the repetition code, as it's often called. So the idea of the repetition code is pretty easy. Imagine what we've got is we've got a bit, right? So our bit value is, either 0 or 1. And now the way that we're going to envision modeling a noisy computation is that imagine with probability p a bit flip occurs. That is, we end up getting x goes to not x for any variable x. And so this is what we're going to have. And we'd like to be able to build some redundancy into this. So the simplest way to build redundancy is to do the following encoding. We will end up saying that we're going to encode 0 as 3 zeros and 1 as 3 ones. Okay, we'll see in a second why I pick 3 rather than 2. But this is the simplest sort of repetition code. And so the idea basically is the following. Let's envision that an error actually ends up happening. Well, the error, let's say this bit ends up getting flipped randomly. That will end up causing this code word over here, 0, 0, 0, to go to 0, 0, 1. Similarly, 1, 1, 0, or sorry, 1, 1, 1 will map to 1, 1, 0. Now, by taking a look at the structure of this, we can see that there's 2 zeros and 1, 1. So therefore, this is closer to the original code word that we had, versus this over here, which is closer to that one. Now, these two are completely distinguishable. However, if we ended up having 2-bit flip errors, we could end up getting something like 0, 0 goes to 0, 1, 1, which is actually closer to this over here. This would correspond to what we call a logical error, where the errors in the redundant encoding of the bit accumulate to the point where our decoding process ends up saying that actually we're more likely to be the other bit string than the former one. So that's basically the idea behind this. Now, to see formally what we end up meaning by this, it's actually nice to think about this in terms of probability. So we can think about this, say decoding the 1-bit flip case. So in the event that let's say we measure 0, 0, 1 coming out of the repetition code. Well, under this assumption, the probability that we end up getting this, and assuming each bit is IID, is independent and identically distributed. Okay. Say we measure 0, 0, 1. What we want to be able to do is we want to be able to compare the likelihood that this would end up coming up. The probability in this model that we would generate 0, 0, 1, given that 0, 0, 0 is the true one, is equal to the probability that we don't flip on the first one times the probability that we don't flip on the second one times the probability that we flip on the third. Conversely, the probability that we would have gotten the same thing given that we have 1, 1, 1, probability of drawing 0, 0, 1, given that the truth was 1, 1, 1, is equal to, well, we need to flip now the first 2 bits, but leave the last one the same. So this would be P times P times 1 minus p. So you can see in this case that the likelihood ratio is in the ratio of probability between all of these is actually just going to be 1 minus p over p. So in this particular case, let's consider comparing to the case where we just have the bare qubit. If we had the bare qubit, bare bit, we'd have 0 and 1. Now this is going to flip to 1 with probability p, and this will flip to 0 with probability p. So the probability of an error occurring over here is just simply p. And the likelihood ratio that we end up getting for this is going to be simply, yeah, okay, never mind. So the point is that this likelihood ratio that we end up getting over here for p less than 1/2 is greater than 1, meaning that in the event that p is some small value, like let's say that p was equal to 1%, then what we would have is we would have with overwhelming probability, this is the more likely model than that one, meaning that it's much more likely that the data came from one error happening on 0, 0, 0 than one error happening on 1, 1, 1. So that's how we end up doing it. And in the event that we decide that this is the correct course of action, then based on this likelihood ratio test, we say, okay, the third bit is the most likely one to have flipped, and therefore we can do a correction. We can just take the bit string and flip the third bit to end up getting 0, 0, 0 back up. So that's how this whole decoding process ends up working. But you might think, okay, well, 1% is pretty good. But, you know, maybe we want more certainty. Is it possible to systematically improve this? And the answer is, yeah, it is. So the way that we can do this is we can actually consider more general repetition codes. Let's consider the having 0 go to 0 to the n, and 1 go to 1 to the n. All right? In the event that we end up having this, and let's say that we were to take a look at a bit string and measure the analog of this. So let's say we measure n minus 1 zeros, and the last bit is flipped to 1. Then the probability of generating this bit string of n minus 1 zeros and 1 1, given that the true should have been n zeros, that is equal to, well, just 1 minus p to the n minus 1 times p, versus the probability of getting the same outcome if the true bit string was n ones. In that case, the probability is p to the n minus 1 times 1 minus p, which ends up giving us a likelihood ratio of 1 minus p to the n minus 1 times p over 1 minus p times p to the n minus 1 equals 1 minus p over p now to the n minus 1. And minus 2, I'm sorry. So that is how this ends up going. And you can see that provided 1 minus p is less than p, i.e. if p is less than 1/2, then at that point, this likelihood ratio will increase exponentially. Okay? So what that ends up meaning is that with overwhelmingly high probability, saying that this state over here actually corresponds to that one will become exponentially more likely. So what that means is that if we want, under this error model, the probability of guessing error wrong is, if we want that to be equal to delta, then basically what we end up getting is that, well, delta then is equal to 1 minus p over p to the n minus 2, which ends up meaning that we end up getting, probability, that's a likelihood ratio. I want the probability of guessing incorrectly in this case. So the probability of guessing incorrectly will be p to the n minus 1 times 1 minus p. Okay, and therefore we end up getting delta over 1 minus p log of this is equal to log p times n minus 1. And so therefore implies that taking a value of n in order log delta over 1 minus p will suffice for ensuring that this ends up working. So what that means is that we don't require that much redundancy in order to make the probability of us erroneously decoding a bit flip error arbitrarily small. So that's fantastic, actually. And this is basically the essence of where the classical stuff ends up getting its power. And by the way, it should be mentioned that this form of a repetition code is used frequently in ordinary computers for, it's used frequently in communication, and also variants of this are used in the parity check protocols that are often used in memory. So now that I've discussed this, let's dive a little bit deeper into terminology. Okay, so what we were doing above is we were just exploring what is possible with repetition codes and showing that if we throw more redundancy at an individual problem, then the probability of us incorrectly being able to identify which bit or bits got flipped ends up shrinking exponentially. This actually has something to do with a concept called code distance. So a code has distance d if for all code words in the code w and w prime, it takes d errors to go from 1 w to w prime. Okay, here's an example. Let's take a look at the 3-bit repetition code that we considered before. And again, so far, nothing here is quantum. This is just ordinary repetition codes. We have that 0 goes to 0, 0, 0, and 1 goes to 1, 1, 1. Okay, this is a distance 3 code. And the reason why it's distance 3 is because we need to have an error on this site, and this site in order to transform the two code words in here into each other. Okay? So that's why this is a distance 3 code. And a property of codes is that a distance decode can correct at most d minus 1 over 2 errors. Okay, so, and by errors what I mean is in this case, flips in the physical bits that end up constituting what we call our logical bit over here, which is the code word, effectively, that we're trying to represent using our physical bits. Now, let's take a look at this. I've got a distance 3 code here, so this implies that the repetition code here can end up getting, well, d minus 1 over 2 is equal to 3 minus 1 over 2, which is equal to 1. So this code can actually correct at most one error. Why is that, you might wonder? Well, we can see this just by looking at the code. And also that example that I did previously. So let's say that we're subject to 2 errors, right? We would map this to 0, 1, 1. Now, on the other hand, if we had 1, 1, 1, the 0, 0, 0 requires 2 errors in order to be able to get to 0, 1, 1. However, this requires only 1 error. So what that means is that if we take the maximum likelihood estimate as the estimate of what error actually happened, we would say, oh, well, it's clearly this one, because this is going to be better by a factor of p, roughly. However, if we knew a priori that there were 2 errors, we would have made a mistake if we decided to try to correct this bit flip by flipping that to 1. We would have started with our code word 0 over here, and by doing that correction, we would have mapped it to 1. Okay, so that's why we can only correct a distance of d minus 1 over 2 errors, because in the event that we have, basically, imagine we've just got 2 code words over here. Once we end up getting a distance, a Hamming distance, effectively in this case, beyond our code word w and w prime, then we start becoming closer to the other code word than the previous one, which is why we end up having this property. Okay, so that is what we mean by code distance. Now, often in the literature, you'll end up seeing the following notation, and I just wanted to mention it because sometimes it can show up and trip people up. We could say that a code is called a NKD code if it uses n bits to encode k bits with distance d. So, for example, the repetition code that we considered above, which is just 0 going to 0, 0, 0, this has an n of 3 over here. It has a value of k of 1 because it encodes 1 bit. And, as mentioned before, it has distance 3 over here. So this would be an example of a 313 code. Okay. Now, on the other hand, if we ended up having the simpler code, 0 goes to 0, 0, and 1 goes to 1, 1, the distance would be equal to 2 in this case. And that would correspond to a 212 code. Also, I should mention in this case, we cannot correct errors. However, we can detect the presence of them with this code. So even codes that can't correct errors like this one still can be useful, because sometimes they'll let you know that an error in fact happened. So that's basically it. And in general, as I mentioned before, the probability of having an error that you can't detect or correct using these schemes shrinks exponentially with the code distance over here. So that's basically how the classical case ends up going. Now, quantumly, what we're going to want to do is we're going to want to deal with a couple of challenges. Quantumly, the biggest challenge that we're going to want to deal with, and people actually thought that this would be a deal breaker to begin with, is the problem of measurement. So, if we ended up having a state, right, let's say 0, and I'll be very clear, often what we'll do in quantum error correction language is we'll put an L down here to mean that this is the logical state corresponding to a physical state. Okay, this, if we were to try to use the repetition code, would be just, say, 0, 0, 0. Okay, and we'd have 1 logical equals 1, 1, 1. So this is the exact same thing that I ended up doing with this rule here, except I'm applying the same thing in the quantum world. All right, so let's say that what we have is we have a bit flip. Okay, and the way that we would have this is could envision this as a quantum circuit. Ideally, we'd like to be able to do take in a particular code word, let's say it's 0, but we have an error over here, which is an X gate. This is an error. We don't want to have this X gate, but because of a hardware imperfection, that bit got flipped partway through. Okay, so what we would like to be able to do is we'd like to be able to detect it. So we could just measure. All right, all of these at the end, and then we would end up seeing that flying out of this comes 0, 0, 1. Well, let's fix that then just by simply re-preparing the state, 0, 0, 0 over here, and done. Life is good, right? But what if our state was of the form A0 logical plus B1 logical, which is equal to A0, 0, 0 plus B1, 1, 1. Well, in the event that we measured all of them, we would project to either this case or that case, thereby damaging our system. So at first glance, because measurement of all of these different bit strings over here seems to give us information about which possibility we're going through, it seems at first glance that error correction actually is entirely antithetical to the idea of quantum computing. But actually that isn't true at all. In fact, we can measure all of this information without revealing any of the salient information about the bits. For example, let's now just forget the measurement and look at what ends up happening in this case, where we end up putting now our state psi in through this circuit. Well, what we would end up getting out is we would get a 0, 0, 1 plus B 1, 1, 0. Okay, fantastic. So now, obviously, if we measured every single bit here, we would learn whether we're on this branch or that one. Instead, let's take a look at a different property. Let's take a look at the parity between the individual bits. So if we instead measured the parity between these two, the parity of these two bits would be 0 exclusive OR 0 and 1 exclusive OR 1. That's equal to 0. That gives us no information about whether we're on this side or that side. So we could measure the parity just fine without distinguishing those two states. Okay, great. Now let's envision that we do the exact same thing and we measure those parities. Well, in this case, we would get 0 exclusive OR 1 and 1 exclusive OR 0, which in both cases is equal to 1. So by measuring the parity, we would have learned, in this particular case, that these two bits have the same value, but those two are flipped. And so what we can do is, from this information, we can infer, oh, well, if these two are consistent and that one is flipped, then the most likely model is that this qubit ended up having an X error associated with it. So what we would do in that case is we would begin with some block that would measure parity, or the parities of all of these individual bit strings, and based on these particular outcomes, what we will do is we will apply, in this case, we will apply an X gate to flip that third qubit where the error ends up happening. Okay, this data over here is called an error syndrome. Okay, just like, you know, we talk about illnesses being syndromes, we use the same terminology for errors. This information through the parities ends up coming back and allows us to work backwards and figure out what the most likely error is, and then we can correct it. It's important to note, physically though, if we were carrying this out, this error correction step requires inference from the syndromes to figure out what the correct, in general, correction block that we should put in afterwards in order to deal with it. This part over here requires substantial, not as substantial as it once did, but it still requires substantial compute to make this happen. So in practice, what ends up happening with quantum error correction is that you kind of have this hybrid system where you're getting an ordinary classical computer to process and interpret the measurement outcomes from the quantum computer and then figure out what the most likely errors are and intervene and correct. Okay, so that's the idea. And incidentally, in practice, actually, often these X gates over here aren't even applied. In practice, we just redefine our frame of reference and recompile the rest of the calculation around the fact that we know that this bit has been flipped. And that way we can save any errors that would come in by trying to flip the bit again. So that's just it's a kind of a cute trick that people do in practice. But at a high level, we can always envision the error correction operation as physically correcting each of those individual errors. Okay, cool. So now that you've got an idea about how all of this works, I'm going to zoom in a little bit more on several of these steps. So basically, in every error correction protocol, there are kind of 3 stages. The first stage is the encoding stage. Second is the syndrome detection. decoding phase. And then the third one is the correction. Okay, so let's just deal with the encoding phase, and specifically looking at this this repetition code that we've been talking about. So the encoding procedure for the repetition code is actually as follows. So let's say we start with the state A0 plus B1 over here, and we want to encode that in our system. We're going to begin with 2 quantum bits over here set to 0. Now the easiest way to do this, and perhaps most natural, is this over here. Okay, so once we end up doing this, then it's very easy to see what the state that we would end up getting out the other side would be A00 plus B111. Okay, cool. So now we've encoded this. Since both of these are our code words, you know, they're like W and W prime using the above discussion, we've now encoded this inside our quantum error correcting code. Okay, cool. Now, there's some other options to this that I should mention need to be thought of in order to make this happen. So another option that we could have done is we could have considered following circuit for encoding. Okay. This over here. Now, both of them will end up mapping A0 plus B1, 0, 0, to the exact same thing over here. But within the error model that we've posited, this one actually is way, way better to do than that one. Which seems kind of strange because physically they look very similar, and on top of that, because this one's only using nearest neighbor interactions, it looks like this might be even easier to engineer. But despite that, this is actually the better option. The reason why can be seen as follows. Okay, let's look at the simplest case. Let's look at the case where we have an error on the third bit. Okay, we can always envision that error occurring in the following way. Let's say that there's an X gate that ends up flipping it. Okay, now if we do the same thing over here, we can end up seeing that this will have the exact same effect as this over here. The reason why these two are equal is because of the fact that naught commutes with the control naught, at least on the target. So therefore, this is equal to, and by the way, commutes, two matrices again, commuting means AB equals BA. So we can switch the order is all I mean by commuting. So this is equal to that. Similarly, this is equal to this over here. In both cases, we have one error coming in, and we've got one error coming out. All right, cool. So it looks like they're kind of the same, but now let's assume that this error happens in the second qubit, not the third. So in that case, what we would end up having is we would have X control naught and X going down here, and this one, using the exact same logic, will end up giving us one error popping out the other side. Now, if we do the same thing with the other case, we would end up having X coming in here, going down there. Now, X does not commute with the controls of a C0 gate. Using our circuit identities, we can end up showing that this is equal to that. So in this case, two errors come out. And so this is a bad, bad thing to have. if we want to have a encoding that's robust to bit flip errors, because of the fact that it has this possibility for one error on the input to end up propagating to two errors on the output. So that is why this circuit over here is generally considered to be the better option. In general, what we want is we want to have circuits that don't unnecessarily propagate errors are called fault tolerant. And a lot of the work that comes in to the quantum error correction field is really boiling down to finding good circuits that can tolerate errors of this like this. Okay, so what we want to do is we want to build up fault tolerance in our encoding and our decoding schemes. So that is how encoding ends up working for the repetition code. We basically just end up using a transformation of this form over here in order to be able to take an input state in an unencoded form and then transfer it over to its encoded version. Great. Now, let's take a look at the next aspect of this, which is we would like to be able to measure the syndromes, i.e. decode these values. So there's a number of different ways that we can end up doing this. Now, the way that I prefer to think about this is that let's envision the error detection / decoding step. Okay, so say we've got a situation where we have, our repetition code, which is, our qubit encoded in the 313 code is going to be this over here. Now, what we can do is we can let's say we take a look at the different types of physical errors that we can end up having. We could have no error. We could have one error. However, we can never have two errors, because in the event that we have two errors, as we said before, our decoder will end up saying it's more likely that the code word that we're seeing came from the other side. So that means that we only are going to have to worry about these two cases over here, because the two error case can't be handled by this distance 3 code. So we've got no error and one error. There's actually 3 possible errors that we could end up seeing for this. We could end up seeing an error on the rightmost qubit, which would be given by an IIX operation. We could see an error happening on the second one, or we could see an error happening on the first one. And of course, if there's no error, that corresponds to the identity transformation being applied to all 3 qubits. So that is what we would like to do. So if that's the case, then what we can do is we can consider a projector onto each of these different cases in order to be able to see whether or not we have, say, no errors. So a projector, which we can use, I'm going to call it p hat 0, that is going to project us onto the 0 error space. I can write in the as the following matrix. Okay, and now this has the property that if we take the no error projector and act it on the quantum state that we assume, or the ideal error-free quantum state that we have in here, this will end up giving us actually just a 0, 0, 0, because this is the only term that ends up hitting that, and this and that have inner product 1. So that ends up leading us to that, plus B, 1, 1, 1. So we can see that this projection operator, no error, acting on this state over here, actually really corresponds to, honest to God, the real state that we want. Okay, great. So that would be the no error projector. And so if we want to do this, basically what we would like to do is we'd like to find some way of implementing this projector or other projectors like this. Similarly, we can define the error, I'll call it IIX, meaning the projector onto this case over here. That would be the projector 0, 0, 1, 0, 0, 1, plus 1, 1, 0, 1, 1, 0. Okay, and so that is how we can build these things up. And by applying or measuring these projectors, we can identify which of these individual error spaces we're in. Furthermore, actually, measurement of them is actually going to project us onto one of those spaces. And that will give you a bit of a hint about how we're going to be able to handle generic errors when we go forward and talk about the Shor code, which is a generalization of this idea. But in any case, this is what we would like to do. Now, problem is that I haven't really discussed how we could measure how we could measure a projector directly, right? We've already discussed how we can figure out the probability of some configuration. The probability of no error, for example, for an arbitrary state psi is equal to psi p naught hat psi. So we have worked with these sorts of objects before, and we can figure out what for a particular system, what the probability of measuring no error in our output qubits is. It's just this guy right here. That that projector, though, is something I still haven't described how to operationalize. So let's take a look at building this particular projector. The easiest way to do this is, what we would like to do is something. Let's say what we could do is we could write the projector p naught hat is equal to AU1 plus BU2, so on and so forth. And this over here, I'm going to call a linear combination of unitaries, for reasons that are not totally super clear at the moment, but will be later on when we talk about quantum simulation. But once we have a linear combination of unitaries expression like this, then we can always write this as A psi U1 psi plus B psi U2 psi plus so on and so forth. Now, if we want to figure out the probability that, that when we measure, we would end up seeing no error, we could actually estimate all of these now using a Hadamard test. The Hadamard test, recall, is of the form, it looks very much like an iterative phase estimation circuit. It would end up taking the form like this: psi H And if we were to measure this bit at the top, the probability of 0 is just 1 plus the real part of psi u1 psi over 2. Okay, cool. So that's kind of nice. But actually, we can do a little bit better than this. What we're going to do is we can actually further express p naught hat as sum over ai, ai, pi, where these pi's over here, these are Poly operators. So what I mean again by that is I mean these are all operators of the form like I tensor x, tensor y, tensor z. So it's just a bunch of tensor products of x, y, z, and identity is what I mean by pi over here. Now, it turns out that one of the reasons why this is quite nice is because of the fact that all the Poly operators in this decomposition end up having eigenvalue plus minus 1 because pi squared equals identity. This implies that the eigenvalues in question are equal to plus minus 1. Okay, so this actually ends up making the Hadamard test even more convenient than we had before. So, because the eigenvalues are equal to plus minus 1, we can end up taking psi, and we can write it as psi times identity psi. Nothing's changed by that, but we can write identity as a projector onto the positive eigenvectors of pi plus the projector onto the negative eigenvalues of ei, because basically the system, since every eigenvector of each of these unitaries has eigenvalue plus 1 or minus 1, the projector of the identity operation has to be the projector onto the ones that are plus the projector onto the ones that are minus, because that then covers the entire space. So we have the following. Now, if we end up then having that pi acting on p plus psi, this by definition is just equal to p plus psi, because this is the positive plus 1 eigenvalues of pi. So I could also write this as just like plus 1 times that. However, pi times p minus psi is equal to minus 1 p minus psi, just by the definition of the fact that p minus gives us the component of psi in the -1 eigenspace of the Poly operator. So if we end up having that, then going through the algebra for the Hadamard test over here, we end up getting that 0 Hadamard controlled pi Hadamard over here for state psi ends up yielding 1/2 I plus 1/2 0 I plus pi psi plus 1 I minus pi psi. Okay, great. Now, this, using the exact same reasoning, is equal to 1/2 0 I plus pi now times p plus p minus. Just remembering that this is just a fancy way of me writing the identity matrix, plus 1 times I minus pi, p plus p minus, acting on the state psi again. All right, cool. You might wonder, why the heck did I do this? Well, I did this because of the properties of pi. Let's take a look at 1 plus pi acting on p minus psi. Well, using these properties up here, that is equal to 1 minus 1 p minus psi equals 0. However, 1 plus pi, p plus psi, is equal to 1 plus 1, p plus psi. So this actually is equal to simply 0 p plus psi plus 1 p minus psi. So by measuring this qubit over here, we're capable of projecting our system onto either the positive eigenspace of the unitary we're measuring, or the negative eigenspace of it. And we're going to use that trick in order to be able to actually implement these projectors that we're interested in. So the way that we're going to do this is we are going to first, let's take a look at the Poly Decomposition again that I was mentioning. Poly Decomposition gives us a way of expressing this no-error projector, for example, into a sequence of Poly operators that we can then deal with. So the expression, let's take a look at the case where we're doing a no error on p naught hat is equal to 0, 0, 0, 0, 0, 0, plus 1, 1, 1, 1, 1, 1. Okay, great. Now, what we want to do is we want to represent this in the Poly basis. And the way that we're going to do is just, again, using the inner product form. This is equal to, now in this case, sum from I equals 1 to 63 of AI pi. Now, you might be worried, hey, is this guy going to go through and actually figure out all of, oh, sorry, this is 0 to 63. All 64 components that we end up having in here? Well, the answer obviously is no, because I'm super lazy. So what we're going to do instead is we're going to actually just reason about what these are. Now, the coefficients AI are, of course, given by the inner product relationship for Poly operators. So basically what I'm just doing is I'm using the fact that Poly operators, like these PIs over here, form a operator basis with respect to the trace. And so you can find this by computing the trace of the product of the projector p naught hat against pi, where the trace of a matrix, trace of, let's say, A, B, C, D, that's equal to simply A plus D. So it's just the sum of the diagonal elements. Okay, and D here is the dimension, in which case this is 1/8 then. Okay, so we can see immediately that this is just 1/8 of the trace of 0, 0, 0, 0, 0 over here, pi plus trace of 1, 1, 1, 1, 1, 1, pi. Okay. Now there's a property with the trace of matrices, and here I use the fact that the trace of A plus B is equal to the trace of A plus the trace of B. This is obvious just from the definition of what the trace is. The property that's a little less obvious is that if you have the product of two matrices, the trace of the product is the trace of the product in the opposite order. So using that linear algebraic property, we can actually end up cycling this. We can end up writing this as 1/8. The trace, I'm going to cyclically permute half of that projector onto the other side. So this is just 0, 0, 0, pi, 0, 0, 0, plus trace of 1, 1, 1, pi, 1, 1, 1. Okay, but these are just scalars. So this is a 1-by-1 matrix, and the trace of A, if that was our entire matrix, that's just A. So we can drop the traces. And this is just 0, 0, 0, pi, 0, 0, 0, plus 1, 1, 1, pi, 1, 1, 1. All right, great. So now, just looking at this, we can immediately rule out any component of the PIs that have an X or a Y in it. The reason why is because those would end up leading to bit flips in one of these locations and thus have zero inner product. So we know that PI over here, PI has to be composed of only I and Z. Furthermore, just taking a look at this form over here, we can see that any term that has an odd number of poly Zs is actually going to yield 0 over here. The reason why is that if we have Z acting, let's say we have PI was I, Z. Well, computing this expectation value up here will end up giving us +1. However, on this other side, we would end up getting +1 from the first one, +1 from the second one because they're both identity, but the third one will give us -1. So these two are going to cancel, giving us 0. Any term from symmetry that has only one poly Z is similarly going to contract out to 0. Therefore, the only ones that remain are the possibilities with 2 or 0 Z's. And so we can end up seeing actually that this ends up taking a form 1/4 identity plus I Z Z plus Z I Z plus Z Z I. Okay, this identity term doesn't matter for our purposes. The things that we need to take a look at are these. So now, what we can do is we can project onto P0 if we can project onto ZZ, ZIZ, and ZZ. And the way that we do this is by using a Hadamard test in order to try to project onto the +1 eigenspaces of all of these. So the way we do that is as follows. We take our input state, psi, over here. We do the Hadamard test in a piecewise fashion. Oh, whoops, sorry. We begin with psi over here, and we compute the Hadamard test by preparing 3 extra bits off to the side. We apply Hadamard transforms here, and then what we do is we just go through this pattern. So first I'm going to apply 2 Z's here. Okay. Next, what we're going to do is we're going to do the next one, which is ZIZ. So I'll project onto that. And, oh, whoops, here. Nope. There. Yeah. And then finally, I'm going to go here, here, and not there. Okay, yeah. And these guys fly through. Now I Hadamard, 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 and measure. Okay, in the event that I project onto the +1 eigenspace of each of these, that corresponds to applying IZZ plus ZIZ plus ZZI. And that is equal up to an identity to P naught hat. So, in the event that all of these guys come back measuring 0, that corresponds to no error. And then you rejoice. However, in the event that one of these comes back as 1, let's say the third one comes back as 1. Then what we've done is we've projected onto the +1 eigenspace of this one, the +1 eigenspace of that one, but the -1 eigenspace of this one. Meaning that in this case, the first two, or the last two, are correct. So these two are consistent. These two are consistent. However, these two are not. So this corresponds to a single error that we can then track back using the similar orthogonality considerations and figure out what error we exactly are going to have. And then we apply corresponding X gate. I think it's to this one over here. And conditioned on that. So this is the syndrome extraction. And the final step that I discussed involves the correction. And this is how we can end up doing quantum error correction for the bit flip. Okay? And if we wanted to do this with even more redundancy, we could just simply repeat this with a couple more lines. In which case we would just simply have more patterns to end up going through in order to be able to infer this, what errors did happen based on all of these Z measurements. So the biggest weakness about this is that it clearly cannot deal with every type of error that we could conceivably have in this system. For example, let's say that what we have is we have the A000 plus B111. Now, if I end up, instead of applying an X gate on the third bit, I applied a Z gate on the third bit. Then this would end up mapping us to A000 minus B111. Okay, now we would send this through all of this over here. We note because all of these bits haven't flipped over here, we would end up getting, actually, all three of these being 0. And this would go through the quantum error correction phase and literally be decoded as that state over there. And this state is not correct. The sign on the second code word, the logical 1, is opposite of what it should be. So what that means is we've got a major problem, that there are physically important errors that just simply having a bit flip correction, will not be able to address. And this is something that is unique to quantum. And we'll see next lecture a technique for dealing with this. And the idea basically is that what we can do is by using Hadamard transforms, we can convert this phase flip into a bit flip. So we could also come up with a quantum error correcting code to be able to deal with the phase flips. But if we did so, we would lose the ability to correct the bit flips. So by concatenating the two codes, one on top of each other, it's actually possible to create a 9-bit code that's capable of tolerating both a bit flip and a phase flip. It turns out that actually, if we have generic uncorrelated errors in our quantum bits, we can actually use this in order to project ourselves to a discrete combination of bit and phase flip errors. And that's what I'm going to be showing you next time. I'm going to be showing you how you can end up building the shortcode, which is the first complete quantum error correcting code that can be used to deal with this. So yeah, that's basically it for today. Thank you very much, and I will see you all next time.